Hi, I'm Hakim Demay. I will present to you some of the concepts of the implementation of Vaucanson 2. I am from EPITA Research and Development Laboratory. This is joint work with Alexandre Durelut, who is also a member of the EPITA R&D Laboratory, with Sylvain Lombardi from the Bordeaux Computer Science Research Laboratory, and Jacques Sakharovich, who is from CNRS and Telecom Paris. So, first, what is Vaucanson? Vaucanson is a general-purpose platform for Automaton transducers, and more precisely for weighted automata and transducers. It aims at being generic. Being generic means that we want to be able to deal with acceptors, the usual automatas, but also with transducers. We want, of course, to support rational expressions, and any kind of weight. Usual automata and rational expression are over booleans, but we also want to be able to work on integer with less common operations such as minimum and plus, as addition and multiplication. We also want to be able to work with fraction, real numbers, and we also want to be able to use rational expressions as weights. The labels can be implemented as chars or integers, and there are many different kind of labels. We want to support automata whose labels are letters, but labels could also be words or letter and spontaneous transition and so forth. We don't want genericity to be at the expense of performances. So Vaucanson 2, as its predecessor, Vaucanson 1, is implemented as a C++ templated library. No dynamic polymorphism, that is to say, no use of the keyword virtual is made in Vaucanson. Of course, this is not enough to be efficient. We also are using efficient data structures and state-of-the-art algorithms. However, and this is a strong difference with what was done in Vaucanson 1, the first generation of the project, we want to be flexible and offer a nice interface on the top of our strongly typed and templated library. So we want to provide a dynamic interface, a dynamic API, which will deal by itself with the different kinds, the different types of automata, rational expression that we will use. And we will also provide TAFKit, which is a third API, a third level API, which is just a set of tools to be able to manipulate words, automata, rational expression, weights, and so forth from the shell. TAFKit will be an excellent opportunity to discover what Vaucanson is exactly. So, as a quick demonstration of what Vaucanson can do, let's first consider how we save and load automata. Here we're using GraphViz, the well-known package to display graphs, for input and output of automata. As a first approximation, automata can be seen as just graphs, and here you have a plain dot file which describes a graph which is right here below. That graph can be understood, can be read as an automata, provided that we have some conventions. One convention is that I is a special state that designates what are the initial states. So 0 is the real initial state of this automata, and 1, from which leaves an arrow to a special state denoted F. 1 is the only final state of this automaton. So these are the states in circles. There are also transitions, or to be more precise, here just edges, just arrows. we have an arrow from 0 to 0, which has two labels, the label 0 and the label 1. This is to be understood as two transitions from 0 to 0, from state 0 to state 0, one being labeled by 0 and the other one being labeled by 1. Here you have a transition that goes from state 0 to state 1, which is labeled by the label 1. And here something different. We have two arrows, one arrow going from 1 going to 1 labeled by 0, and another arrow from 1 to 1, which is labeled by 0 and also by twice 1. Vaucanson is working with weighted automata. That is to say that compared to usual automata theory, labels can have a weight in a given semmering. Here the semmering is z, with the usual addition and multiplication as operations. So this is almost an automata. What is really missing is information about what is the alphabet of this automata and what exactly do you mean by the weight 1, what do you mean by the weight 2, what kind of operations apply on these guys. This is why in Vaucanson we add a field which we call the Vaucanson context, which provides typing information about automata in dot formats. This information says three things. First, LAL means labels are letters. That is to say, this automaton must be read as the traditional kind of automata. That is to say, its labels are not words, there are no spontaneous transition, it's just NFAs. Label are letters. Second, what are the letters? The letters are implemented as characters in C++, and there are two characters that are allowed, 0 and 1. Third, the weights is in Z. The weights are usual integers. If we had to write, or if you wanted to write what this means, what the context means, it means that transitions can be read as functions going from the set of labels. The possible labels are just the letter 0 and the letter 1 to the set of weights Z. Once you precise the type of the automaton, you can use it with Vaucanson. Vaucanson can read this file and will understand that you are designating a particular automaton. Before we see how Vaucanson deals with this automaton, please have a look at this rational expression. This rational expression represents the language of this automaton. You can see that the fact that states 0 has a loop on 0 or 1 means that we start with any number of 0 or 1, 0 plus 1 star, and then we require 1, 1. We require 1, 1, and then we have any number of 0 or 1 being having 2 for weight. 1 has 2 as explicit weight, and 0 appearing once here with the implicit weight 1 and second time with the implicit weight 1. Of course, it's the same as having 0 with the weight 2. So what happens if we provide Vaucanson with this automaton? First, we can call the unique command of DAVKit, which is VCSN, and ask for a treatment. There's a number of Vaucanson commands that you can call thanks to VCSN, the simplest of them all being cat, which just takes an input and produces it on the output, after having interpreted the input and redesigned the output. So here you can see exactly what kind of output you would get if you provided Vaucanson with binary GV, the file we just saw in the previous slide, and here we ask it to save what it has understood of the file binary.gv into the file named binarycatted.gv, which is depicted here. You can see that the fake pre-initial state I and the fake or invisible post-final state F have disappeared. There remains only 0 being an initial state and 1 being the final state. What else can you do using TAFKit, the set of tools to call from the shell? From Vaucanson, you can ask for the product of two automata, the left automaton, the right automaton, and save the results in a third file, here named squared binary, since we are multiplying the automaton binary.gv by itself. Since the product computes the Automaton product of these two of the two languages, this corresponds to computing the square of the weights. Indeed, if you evaluate 101 on the initial automaton, you will see that it computes 5. If you have a close look at this automaton, you will see that it decodes a binary number into its value. If you provide it with a binary coded number, it will evaluate it into its integer value. So if you evaluate 101 using binary, you will get 5, 4 plus 1, and of course if you evaluate 101, which is 5 on squared binary, you get the square of 5, 25. When you type the context, you type two things. You type the labels. You specify what kind of labels you can use. We saw labels being 0, 1 in the alphabet 0, 1. Here an example where the alphabet is A, B, C, D. We also specify that labels are letters. We could have said that labels are words, in which case, if you look at another command from TAFKit, which is standards, standard is taking a rational expression and builds an automaton from it, the standard automaton from the rational expression. In the LAL, labels are letters context, you would get this automaton, and if labels are words, you'd get this automaton. The second information that the context provides is the kind of weights. We've already seen Z to denote the usual integers. We could also have used Q for the fractions. Here you can see the evaluation of a word on an automaton whose weights are fractions. There's also real, all sorts of different weights, including rational expressions. So here you have an example where each arrow is labeled with one letter, A, B, C, D, and it returns as value a function, actually a rational expression which is labeled by F, G, H and is weighted by Z. This is denoted here. As input we have labels are letters, the characters are A, B, C, D, and the set of weights is the set of rational expressions. What kind of rational expression? Rational expression whose atoms are letters, labels are letters. What kind of letters? Characters, and these characters are E, F, G, and finally this rational expression itself can be weighted by usual integers. Standard is asking for the creation of the standard automaton corresponding to this rational expression. This rational expression says that, for instance, we associate to A the weight E. We associate to C the weight G. And we associate to B the weight twice F, F weighted with 2. 0 or any time. So basically this is a kind of transducer. If we feed it with A, B, B, C, we get E from A, twice 2F from B, and then once G from C. So indeed the result is E twice F, G. And if we provide it with something which is not part of the language, we get 0. This is the 0 of the rational expression, which we display as \z. How does this work? How is it possible that Vaucanson, which is a static templated library, can be used this way with a single program which is able to deal with very different types of automata and rational expression? This is performed by something that we call the static dynamic bridge. How does it work? First, a broad view of the architecture of Vaucanson 2. We have 3 different APIs which are already introduced. First, there is static, which is a low-level templated static library. It's very efficient, somewhat unpleasant to write because there are many details that you have to spell out. Anyway, if you really want to write something very efficient, that's the best place to write your program. But if you want to experiment, or if you want to just use something simple to write simple programs, then you want to be here on top of dynamic, the second API, which is the one that we will explain right now. And if you really want just to toy with small examples and files, something simple, you can use TAFKit, that was just demonstrated in the previous slides. Please notice that TAFKit itself is on top of dynamic. It's very TAFKit programs are very easy to write because actually they're benefiting from the power and flexibility of dynamic. All the magic is here. This is not an API, this is just the bridge, this is just the special routines that glue together the dynamic behavior of Vaucanson on top of the static behavior of Vaucanson. Let's have a look at both APIs, dynamic and static. This will help us understand how they work together, how the bridge binds them together. First, have a look at the static layer. It has 2 strong features. First, it's efficient. It's very efficient because you don't pay any tribute, you don't pay anything to virtual, to indirections. You get excellent performances. And you also get type safety. That is to say that you cannot mix things that are not of the same type. For instance, if you are building an automaton where labels are words, you won't be able to mix it with an automaton whose labels are not words. If you are, for instance, multiplying an automaton of a given type with an automaton of another type, it won't compile. This is type safety, static type safety. The compiler will not let you mix things that cannot go together. Here we have a simple example, running example, which we called prod eval. How does it work? It takes 2 automata as actually names of files. LHS and RHS are 2 file names containing automata, and and we will compute the product of these 2 automata and then evaluate word on the product of these 2 automata. In the static layer, that's easy to see, we are in static layer because you can see the template keyword. In the static layer, you have to precise what is the current type, what is the typing context that you will depend upon. Have a look here at the call site. Here we are calling the static version of prod_eval, and we precise that we will work on labels are letters, characters with Z as weights. This is the kind of automata we will work on. Once you precise what kind of context you want to work on, you are able to specify what kind of automaton you will work on. We will work on automata of type labels are letter, charts, and Z as weights. So we are now able to call read automaton file for the first automaton with its specific type. Here the result L as the type mutable automaton of labels are letters char Z. Same thing for R. And then we can call product, not just any product, but exactly product of these two types of automata, which will in turn return an automaton of the same type. This automaton is named product, prod. And then we call eval, not any eval, but precisely eval for this kind of automaton, and we provide it with word. It will compute a weight, a given weight, which we just display, except that a weight can be displayed in a special way. So we actually ask for the set of weights to perform the display by itself. The set of weights knows how to display weights. So this is the static layer. How does the dynamic layer look like? Much simpler. There's no template, this line has disappeared, no template at all. We are just using the din namespace of Vaucanson, and we just say that I read an automaton. I don't care about its type, just read an automaton and deal with the type for myself, please, and store it in L. Same for R. Compute the product, deal with the type of L and R, I don't care, deal with it, store the result in prod. Note that L, R, and prod can be very different automata. Automaton is generic. It's a single type in which you can store many different kind of any kind of automaton. Here we call eval without even specifying what the kind of prod is. We provide it with the word to evaluate, and then we ask for the display of the weight of the result. You may also see that the call site is much simpler, since we no longer precise what is the type of automaton we want to work on. So let's try it. First, we need two automata. So let's start by building two automata. The first one, named A plus B, is the standard automaton for the rational expression A plus B. The second one, named A star, is the standard automaton for the rational expression A star. And I'm calling the static version of prod_eval on these two automata and on the word A. Doesn't work. It fails. Why does it fail? It says that we provided an invalid type of automaton. Indeed, here and here we have built two automata of type labels are letters, characters, this is good, but over booleans instead of over integer weights. So you cannot call this algorithm. In turn, had you used the dynamic one, it would work. It would work, and it does work, and it computes that indeed A belongs to the intersection of these two languages, and B does not belong to the intersection of these two languages. Of course, if those two automaton were over Z mean, over whatever, over any other kind of weight, it would have worked too. So it accepts any kind of type. But not quite any. It has to remain valid. So for instance, it will refuse that you mix types of automata. Here, binary GV is the automaton we started with over Z, and A plus B is this one over B. Vaucanson doesn't know how to make the product between an automaton over Z on one side and B on the other side, so it fails, and that's exactly what you wanted. You want it to work as often as possible, but not more. So, in this algorithm, here you have a call to evaluate a word on a dynamic automaton. Automaton here is actually VCSN : din : automaton. How does a dynamic automaton be evaluated over a dynamic word? This, we know, returns a dynamic weight, but in reality what's going to happen is that the low-level typeful library will actually be called with the exact type of the automaton, that is to say Z automaton. The static automaton here, which is contained in the dynamic automaton, is a Z automaton. The word here is a word over charts, it's not just any kind of word, and it will return a weight, which is an integer. We know it's an integer since we are calling it over Z, and Z is implemented as integers. So how does this dynamic call resolve into a static call? So how does eventually dynamic eval manages to call static eval for a Z automaton? The setup is we have a dynamic automaton, a dynamic word, and a call to dynamic eval with the dynamic automaton and dynamic word, which will return a dynamic weight. How does this work? First, the user is calling dynamic eval over the dynamic automaton and the dynamic word. This is exactly this line. What happens then is that dynamic eval, first thing that it does is ask dynamic automaton for its precise type. What type are you? This is the call for vname, which means what is your runtime type. And the dynamic automaton will answer, I'm a Z automaton. More precisely, but it doesn't fit on the slide, it will answer that I'm a mutable automaton over lal char Z. It answers as a string. This string will serve to query a registry of all the versions of eval. This register will return for the string that describes the type of the automaton, will return a pointer to the bridge that corresponds to this type of automaton. The bridge is the kind of plug that goes from the dynamic world to the static world and back to the dynamic world. So here we get a pointer to the precise bridge for Z automata. So we call this bridge, providing it with the dynamic automaton, the dynamic word. Since that bridge knows exactly what is the type of the automaton, it's a Z automaton, it can extract the static automaton from it, it can extract the static string, the fully typed string and fully typed automaton, and call the evaluation algorithm on this precise type of automaton and string. This will get us the result. Since we are in the static world, we know the result is an integer, and this integer, the bridge, will turn it into a dynamic value, a dynamic weight, and this weight will be returned to the user. In code, how does the bridge work? On top of this slide, this is the dynamic call. the dynamic call will eventually, see the previous slide, receive a pointer to the bridge. This is the bridge. The bridge, as you can see, has a dynamic input signature and a dynamic output signature. So the bridge has exactly the same signature as the eval, but it is templated by the precise type on the automaton it will work on. Since it knows the type of automaton it will work on, it can extract from the dynamic automaton the fully typed automaton. It can extract from the dynamic word the exact fully typed static word. Therefore, it can invoke the fully typed static evaluation algorithm for the automaton, in our case, which will return the type full value, an integer in our case. And now from this integer we want to make a dynamic weight. This is make dynamic weight with technical details. Roughly, a dynamic weight is a static weight plus information to know what is its runtime type. So you can see how eval, the bridge, is making the link between the dynamic evaluation on the top and the static implementation of eval, which we see here. This is how Vaucanson 2 works. So, does it work actually? Well, of course it does, as you already saw in the part about TAFKit, but it's also efficient. Here you have benchmarks which are performed on top of TAFKit. Vaucanson 1 is invoked via TAFKit, Vaucanson 2 is invoked via its own TAFKit, and OpenFST is invoked via its set of shell tools. You can see that for the epsilon, the spontaneous transition removal in this kind of automaton corresponding to the Thomson automaton of this rational expression, with n being these numbers. So for instance, for 1,000 optional a's, the elimination of the spontaneous transition takes more than 10 minutes with Vaucanson 1 and less than 1 minute with Vaucanson 2 and less than 2 seconds with OpenFST. Another benchmark is, for instance, the determinization on a specific family of automata which is well known for the exponential explosion. So here, for instance, this is Ladybird 6, this automaton. If you which is non-deterministic, if you determinize it, you get an automaton of 2 to the 6 number of states. So here, for instance, the initial automaton has 21 states, and the final determinized automaton gets 2 to the 21 states. It takes more than 3 minutes with Vaucanson 1 and a bit more than 1 minute with Vaucanson 2, and about a third of a minute with OpenFST. So there is definitely a room for improvement, for speed up improvements, but we already get much better figures than what Vaucanson 1 provided, although we have much more user-friendly thanks to the dynamic in the layer. As a conclusion, first, Vaucanson 2 is a direct heir of Vaucanson 1. We kept everything we liked from Vaucanson 1, its rich sets of feature, the fact that it supports any kind of weight, any kind of label, etc. But there are improvements. The API, including the static API, is much simpler and it's much faster, as you just saw. But we also provide a new and much more pleasant API to use, the dynamic API. Where are we heading to? Well, of course, Vaucanson 1 was strong on its support for transducers, and Vaucanson 2 has to work with transducers too, so we are working on transducer for Vaucanson 2. We also want to provide runtime compilation, so something I have not said is that Vaucanson 2 is able to work with any kind of automaton or transducer, provided that you have compiled support for it. So in the previous slides you saw that support for Z mean B, and so for weights, for all these weights was ready to use, but that's because we had already compiled it. If you happen to use some new combination of labels and weights that has not been compiled yet, it won't work. So what we want is to be able to launch the compilation of the component once we know the type that the user is using. And if this works, of course, we don't want to stop to providing shell tools. We also want to be able to bind with languages such as Python. That was a presentation of what Vaucanson 2 is able to do. If you have questions, do not hesitate to go to our website, on which you will find various emails where you can ask questions. Thank you for listening.